Hello friends, stereochemistry of E2 elimination reactions. That is our topic for discussion today. As you know, elimination reactions, they have got very high synthetic value. That is for the synthesis of organic compounds containing pi bonds. That is, elimination reactions are used for introducing pi bonds into organic compounds. So, they are used for the synthesis of alkenes and alkynes. What are alkenes? Alkenes and alkynes both are hydrocarbons. Alkenes contain one pi bond, as a double bond, and alkynes contain a triple bond, that is two pi bonds there. Now, there are two mechanisms, as you are aware of all these things. Two mechanisms, E1 and E2 mechanism, just like SN1 and SN2. That is, SN1 and SN2 are substitution reactions, nucleophilic substitution reactions. Now, in the case of elimination reactions, the basic characteristic is that loss of elements. That the elements are lost from the starting material and a new pi bond it is formed here. So, alkyl halides, for example, alkyl halides, it will react with the bases. It will undergo elimination reactions with the Bronsted-Lowry bases. And the elements of HX, that is alkyl halide, then one hydrogen and X. These elements are lost and we get an alkene. So basically these are all base-induced reactions. That is, the most common elimination reactions are base-induced elimination reactions here. Okay, now base-induced means the most common example is the base-induced elimination reactions of hydrogen halides here. Hydrogen halide from an alkyl halide. So these reactions are known as dehydrohalogenation reactions. That is, removal of the elements of H and X. X is halogen. This is known as dehydrohalogenation reaction. This is one of the most common methods for introducing a pi bond. Correct? And for preparation of an alkene, dehydrohalogenation reactions here. This is a base-induced reactions here. That is alkyl halide, it will react with a base just like say OH minus. Then we have got the potassium tertiary butoxide, sodium methoxide, and all these bases are there. Okay, this is the most common method, one of the most common methods for introducing a pi bond and preparation of an alkene. So dehydrohalogenation, it is an example of beta elimination. You know that. So it is the example of beta elimination. Beta elimination means what? Why it is called beta elimination? Because it involves loss of elements from the adjacent atoms here. Adjacent carbon atoms, we can say one alpha carbon atom and a beta carbon atom. So alpha carbon atom, it is the carbon to which the leaving group, that is X, is bonded. Alpha and beta. Beta is the adjacent carbon atom. So this is known as beta elimination. So dehydrohalogenation, it is an example of beta elimination because it involves loss of elements from two adjacent atoms. The alpha carbon atom, alpha carbon atom means the carbon bonded to the leaving group, and the beta carbon atom adjacent to that. So this is the dehydrohalogenation reaction. Now the basic thing, that is what is the basic mechanism here of an elimination reaction. So we can say, so this is our alkyl halide here. This alkyl halide. Okay, so this is the alpha carbon. We know that this is the alpha carbon and this is the beta carbon. So here, this base B. So this base, it removes this proton here. The base B removes the proton on the beta carbon atom. Then it will form Hb plus. Okay, now this CH bond here, the electron pair in the CH bond, it is used for formation of the new pi bond between the alpha and beta carbon atoms here, and X, that is the leaving group, it goes along with the electron pair here. So the resultant product, it is an alkene. Okay, alkene is formed, then we get say Hb plus, then we get X minus. That is the leaving group here. So this is the base-induced elimination reaction. Correct? The base removes the proton from the beta carbon atom here. That is the beta proton. It is removed and Hb plus is formed. And the electron pair in the beta CH bond. So that, it is used for formation of the pi bond. between the alpha and beta carbon atoms here. So the electron pair in the CX bond, it ends up on the halogen atom. It is forming the leaving group. Leaving group is the X minus. These are the basic concepts of elimination reactions. Now we know there are mechanisms. There are two different types of mechanisms, E1 and E2. You know that. Now let us see the mechanism of the, consider a reaction here. Elimination reaction. So E2 and E1 mechanisms. That's the difference here. It is only in the timing here. Okay. So E2 mechanism, that is a bimolecular elimination mechanism, E2 and E1. These are the two types of eliminations here. We know that. So this is these two mechanisms, the difference, because I will not be discussing it in detail. So E2 and E1 mechanism differ only in the timing of the bond cleavage here and the bond formation. That is the cleavage of the bond, heterolytic cleavage of the bond, and the formation of a new bond here. Correct. It is similar to SN2 and SN1 reactions. That is substitution reaction, SN2, SN1 reactions here. Okay. Now, E2 mechanism, we can say that's the most common mechanism for dehydrohalogenation. The most common reaction, E2 mechanism, it is the most common mechanism for dehydrohalogenation reactions here. Correct. So let us see what is the nature of this E2 characteristic, basic characteristics of the E2 mechanism. Then we'll come to the stereochemistry, because it's only a preliminary introduction so that you will have a better grasp of the stereochemistry angle. So here E2 mechanism, let us see how it will look like this. Let us see a compound. For example, we can say tertiary bromide. So tertiary butyl bromide. So this will be reacting with a base, say OH minus here, base. So we'll be getting an alkene here. That is CH3 twice C double bond CH2. So this is the alkene form. Then we get this H2O plus Br minus and all this kind of a thing here. So tertiary butyl bromide, that is E2 mechanism for the reaction of tertiary butyl bromide with a strong base OH minus here. So we'll be getting an alkene. Okay, now this is second order kinetics. We know kinetics, second order kinetics, a concerted reaction here. Concerted reaction means all bonds are formed and all bonds are broken, and all bonds are formed in a single step. Correct. E2 mechanism, it is a single step reaction. Kinetics is a second order kinetics, is a bimolecular reaction. The rate of the reaction, it will depend upon the concentration of the alkyl halide and the base. Okay, it's a second order kinetics, bimolecular reaction. That is, the rate will depend upon the concentration of the alkyl halide and the concentration of the base here. It is a concerted reaction. All bonds are broken and all bonds are formed in a single step. That is the fundamental characteristic of a E2 mechanism, E2 reaction. So how this reaction take place here? Let us examine here. So basic thing I will just tell you here. So this compound, tertiary butyl bromide here, that is CH3, then we have this C, then another CH3, okay, then we have the Br here, then CH2, H, that is CH3, I am putting it in this fashion. So this is our alpha carbon atom and this is our beta carbon atom, correct? Alpha and beta carbon atom, alpha carbon. So this bromide, it goes like this. That is the leaving group here. So the reaction, this proton, correct? The base attacks this proton here. That is OH minus here. So this is the mechanism here. Okay, that is from the beta carbon, the beta proton, it is removed by the base OH minus here, and a pi bond is formed there. Okay, the electron pair in the CH bond, it is used for forming the pi bond between the alpha and beta carbon atoms here. Okay, the leaving group goes along with the electron pair here. So the result here, it will be a alkene here. So this is a new pi bond. New pi bond is formed here. Now the base OH minus removes the proton from the beta carbon. Correct. The electron pair in the beta CH bond, it forms a new pi bond here. Correct. Now, what we are primarily concerned, what is the transition state here? So, how many atoms are involved in the transition state? And what are the bonds which is partially broken and partially formed and all this kind of a thing. You see, that energy diagram we have seen earlier. So, let us see the transition state. Let us draw the transition state so that you will get a better idea. It will be interesting. So, in the transition state, here we can say alkyl halide, say this is CH3 group here. So, nothing happens to this CH3 group. Then another CH3 intact, nothing happens to that. So, what happens? Then this bond, this is the leaving group bond, it is partially broken. Okay, we have 6 electrons here and a partial negative charge here. Okay, then we have this double bond here. This double bond, it is partially formed here. Partial formation of the double bond here with this beta carbon atoms here. Okay, now CH2 here, another hydrogen is here. This hydrogen, it is partially broken. Partially broken in the sense it will be combining with the base here. Okay, therefore this again I am putting it in a dotted line here. Then there will be a partial bond. It is formed with the OH group here. Correct? So a delta minus here. Partial negative charge. So how many bonds are partially formed here? 1, 2, 3, 4 bonds here. Okay, how many atoms are involved here? 4 atoms are involved. So the transition state, we can just draw it in this fashion. That is a double dagger here. We can put it. So 4 atoms are involved here. In the transition, this is the transition state, 4 atoms. Which are the 4 atoms? From the alkyl halide, we can say that 2 carbon atoms are involved here. 2 carbon atoms are there. Then 1 leaving group is there and 1 hydrogen atoms here. Now let us see, this is the preliminary thing here. After having discussed up to the transition state here, now we will proceed with the stereochemistry angle. So, now in the E2 mechanism, we can say E2 reactions. E2 reactions, they generally do not produce the products with a tetrahedral stereogenic center. Okay, E2 reactions, they do not produce products with tetrahedral stereogenic center. So, therefore, it is a transition state. We have seen it consists of 4 atoms that react at the same time because it is a concerted reaction we have seen. Single step, that is the bond cleavage and bond formation, both the things take place simultaneously. Okay, therefore, in the transition state, the 4 atoms that react at the same time here, and they will not react just like that. A particular stereochemical arrangement is needed for this. That is the point which we are coming to now. Okay, that is the general stereochemical features. That it depends upon the transition state of the E2 reaction. Okay, this is the reaction which you have seen here. Tertiary butyl bromide reacting with OH minus. So this is the transition state for this here. So these 4 atoms, they react at the same time and they react only if they possess a particular stereochemical arrangement. Now let us examine what is the stereochemical arrangement here. Correct? Now the transition state of an E2 reaction, it consists of the 4 atoms here. That is 1 hydrogen, then 1 the leaving group. That leaving group, it can be this X, the halogen group here, halogen atom, we can say, and 2 carbon atoms. Okay, now all these atoms it should be aligned or oriented in a single plane. Okay, most important point, single coplanar. All these atoms, that is 2 carbon atoms, 1 leaving group X and 1 hydrogen, all these atoms are aligned in a single plane. Okay, now how is it possible? That is important point for us now. Okay, these 4 atoms of the from the alkyl halide, they are all aligned in a single plane. They are all coplanar. How this is possible? Because there are 2 methods here. One is the CH bond here. That is the carbon hydrogen bond and the CX bond here. Okay, so CH bond and CH bond and CX bonds, both these bonds are to be coplanar. It should be coplanar. That is, they should lie in the same plane here. So what are the basic mechanisms, how it is possible? That is what we are going to discuss now. So one method here, we can say it is, see, we can say H, then X, correct? Then one group behind and one will be on a wedge here. This is a wedge actually. Now another possibility here, will be like this here. Another group here. It is another wedge here. That is this kind of an orientation here. That is the H and X on the same side of the molecule. Correct? Then only it can be coplanar. The CH bond and CX bonds, that is carbon hydrogen bond, and the carbon X halogen bond, CX bond, should be coplanar. They must be lying in the same plane. So one orientation is H and X lying on the same side of the molecule. So this is known as syn periplanar geometry. Syn, it is just like this, syn periplanar. Syn periplanar geometry here. So other mechanism option is C and C, carbon carbon. This will be in the opposite side here. Okay. Like this we can draw. So this is known as, that is here hydrogen and halogen atom. Hydrogen, and this is our hydrogen here, and this is the halogen, H and X. They are on opposite sides of the molecule. So this particular orientation, it is known as anti-periplanar orientation, geometry here. That we have syn and we have anti. Just like cis and trans, we say here syn here means H and S. That is the CH bond and CX bond. It, they lie on the same side of the molecule here. X and X are on the same side of the molecule. That is the syn periplanar geometry. And in the anti-periplanar geometry, H and X are on opposite sides of the molecule. That is known as anti-periplanar geometry here. Now, let us see the Newman projection, how we can draw, then we will understand. So, if we draw the Newman projection, we see that is the syn. The syn one, it is an eclipsed conformation. And the anti one, it is a staggered conformation. So in the case of an eclipsed conformation, we know the dihedral angle. Dihedral angle, it is 0 degree. Whereas in the case of a staggered conformation, the dihedral angle will be 180 degree. That is H and Br, or H and X will be on opposite sides here. So let us see. We will just draw it now. The syn and anti conformations here. Orientations. That is H and X on the same side and H and X on the opposite side. Okay, now if we just draw this Newman projection, we will be getting a better idea. So this is the outer carbon and inner carbon atom. That is how the Newman projection is done. This is the outer one. So here inner one, this one is there. Now we have like these 3 groups we are just drawing here now. That is we can say BRH, whatever it is there. Now here what is more important is here one is BR here. BR is X here and H here. Okay. Now here we get I'll just draw it again. Outer carbon. So what I just want to show you is this eclipsed conformation, how it is getting eclipsed here. This is our X and this is our H here. So here we can say this methyl groups, CH3, whatever it is there. Then we can put it here, this is hydrogen. Okay. So here we can say the dihedral angle here. So this is the syn periplanar geometry. Syn periplanar geometry, that is the eclipsed conformation. This is the eclipsed one. So the dihedral angle here, it will be 0 degree here. Okay. Now if you draw the other one, that is the staggered conformation here. This is a staggered one. Staggered conformation, that is of lower energy here. Here the dihedral angle, it is 180 degree. Dihedral angle here means the CH and CX bond here. Okay, that is the CH bond and CX bond. CX, that is on the alpha carbon atom, that is carbon number 1 or 2, whatever it is there, and the other one. So CH and CX bond, that is the angle between these two bonds here. That is known as the dihedral angle. Here the dihedral angle in the case of the staggered conformation, it is 180 degrees here. That is hydrogen atom and the bromine atom here, they are far apart here. Okay. Now for an E2 elimination here, E2 elimination, it occurs most often in the anti-periplanar geometry. Most important point here, that is called trans elimination, we call it. That is trans elimination. So E2 elimination occurs most often in the anti-periplanar geometry. Correct? Anti-periplanar geometry, that is called known as trans elimination. That is the preferred orientation. Preferred orientation for any alkyl halide undergoing E2 elimination. The reaction takes place in the lower energy staggered conformation. Correct? So the lower energy staggered conformation, that is the anti-periplanar orientation geometry. So E2 elimination, it occurs most often in the anti-periplanar geometry. That is the trans elimination. Okay, that is the preferred orientation, whether the alkyl halide is a cyclic alkyl halide or whether it is an acyclic alkyl halide. The preferred orientation for any alkyl halide undergoing E2 elimination, that is the anti-periplanar. That is the staggered conformation here. Staggered conformation is the lower energy conformation, you know that. Okay, so you know what is the advantage here? This will allow the two electron-rich species, that is the incoming base, that is an electron-rich species, and the leaving group here. You know, it will be as far apart as possible. Okay, so whether it is a cyclic alkyl halide or an acyclic alkyl halide, so this is the preferred orientation for beta elimination here, E2 elimination here. Now let us see the other. This is the Newman projection. I will just show you something similar to the Soho's how this elimination reaction take place there. Trans-elimination reaction. It is known as trans-elimination from the anti-periplanar geometry here. Okay, now here let us see like this. If we have done something like this here, so here we have the H hydrogen here, and this is the Y. That is the leaving group here. X or Y, whatever it is there, you can just write here. Okay, so it will have very important consequences in cyclic compounds here. Okay, now this base attacks this proton here. Now this is the leaving group. Sorry, the beta proton. Like this it will go. Okay, so this can be one alkyl group here or another alkyl group R1. So whatever way you can want to write, you can write it here. Okay, so this is the Y leaving group here. So here elimination of HY here. So what we will be getting here? Elimination of HY. So we will be getting a alkene. This is a trans alkene, because these identical groups are on opposite sides of the double bond here. So this is the double bond. This is an alkene. Okay, this is a trans alkene. Okay, in the case of, say, this is the anti-periplanar geometry. That is a staggered conformation. This is anti-periplanar geometry here. That is H and X on opposite sides of the molecule here. Okay, anti-periplanar conformation, we can say. Now, syn. What will be the nature of the syn? The syn will be, as you know, so this H and so here it is our Y, that is the leaving group here. Then we have our say R1, R and all these kind of things here. Okay, so here what happens, the base, this removes this proton here, then pi bond is formed here, leaving group goes off. Okay, so we will be getting, say, minus HY. So we will be getting an alkene here. This alkene is this is the possibility here. Okay, R1, that is a cis form, cis alkene. So trans alkene is the most stable one, and compared to the cis alkene here. So this is the syn periplanar geometry, and this is the anti-periplanar geometry here. Okay, so this is the anti-elimination. It is a very much preferred elimination here. Anti-elimination, we get a trans alkene. So that is the most stable arrangement. Okay, compared to the syn periplanar, that is an eclipsed conformation, and anti-periplanar, it is staggered and eclipsed here. This is anti-staggered, and this one is syn is eclipsed. That is the difference here. Therefore, now anti-elimination, that is always preferred elimination. Why? Because there is an obvious advantage here. That is, if the elimination is taking place, say, from a conformation, say, in which we have how many atoms here? We have this hydrogen, then we have alpha carbon, then we have beta carbon, then we have this leaving group. Say leaving group here, in this case I have written Y here. So these are the 4 atoms here. Okay, that is, they are all in the same plane. Correct? That is elimination taking place from a conformation, in which the hydrogen, the alpha carbon, the beta carbon, and the leaving group, they are all in the same plane. Then the p orbitals, when these atoms are departing, when during the course of the reaction, the p orbitals will be developed on the beta carbon and alpha carbon. Okay, so alpha carbon and beta carbon, there will be p orbitals as and when these atoms are leaving there. Correct. P orbitals are developing on the beta carbon and alpha carbon. Hydrogen and H, that is the proton and the leaving group, they are all departing. Then these p orbitals, it will be parallel to each other. And when these p orbitals are parallel to each other, there will be maximum overlap. Maximum overlap means the stronger will be the pi bond being formed there. Got the point? That is, when these atoms are in the same plane, the p orbitals being developed, when this H and H plus and Y minus and all departs here from here, then these p orbitals, they are parallel to each other. Then maximum overlap. So what we want in the bond formation, we want maximum overlap here. So maximum overlap. For that purpose, it will be interesting there. Okay. Now, let us see an important aspect of halocyclohexanes. So we have seen earlier the conformations of cyclohexanes and all. So let us see the halocyclohexanes now, how it will look like. That is the elimination reactions in halocyclohexane, E2 elimination in halocyclohexanes. That is a cyclohexane ring with a halogen atom here. Cyclohexane, we know it exists in the two conformations, chair form and board form and all we have seen there. The chair conformation is the most stable conformation there because the angle strain is much less there. Okay, so the chair exists in two forms, that is interconvertible chair forms. We can say cyclohexane exists as two chair conformations, correct, that rapidly interconvert. Okay, now so substitute in the case of a substituted cyclohexane, we have seen the substituent groups in the equatorial position. That is the most stable arrangement. Okay, that is equatorial substituent groups in the equatorial position. That is the more stable one compared to the axial one. Axial and equatorial groups there. We have seen, we know that what is the axial and equatorial and all. Or let us see halocyclohexane here. So this is the chair conformation. Okay, here this is the axial group here. Axial hydrogen, equatorial chlorine. So this is the most stable arrangement. Because more stable because the chlorine is in the equatorial position there. So this will be rapidly interconverting. It will be rapidly interconverting to form okay. So here the chlorine becomes axial here. That is a ring flipping. We have seen cyclohexane chair conformations, they flip, ring flipping. During the ring flipping, the axial group becomes equatorial group and the equatorial becomes axial one. So here the chlorocyclohexane, we can say this is more stable. And this will be less stable. Why? Because the chlorine substituent, it is in the axial position. Okay. So more stable and less stable. That is the chlorine in the equatorial position. That is a preferred conformation. Because chlorine group, it is in the equatorial position, that is a preferred conformation rather than the chlorine in the axial position. Now, for E2 elimination to take place, we have the CCl bond and CCH bond here. CCl bond, CCH bond here. We have these two bonds here. Okay, that is CCl bond and CH bond here. Okay, now for E2 elimination to take place, the CCl bond, it must be anti-periplanar. Okay, that is CCl bond, it must be anti-periplanar to the CH bond on the beta carbon atom. That is beta CH. Okay, this is the beta CH bond here. This will be on the alpha carbon here. Okay, for the E2 elimination to take place, for E2 elimination, the CCl bond, it must be anti-periplanar to a CH bond on a beta carbon atom. Correct? So this will occur only when the hydrogen and chlorine atoms are both in the axial position. So it is known as trans diaxial geometry. Trans diaxial geometry here. Okay, that is the E2 elimination. It will take place only when the CCl bond and the beta CH bond, okay, they are they are actually anti-periplanar. Correct? So E2 elimination, the CCl bond, it must be anti-periplanar to the CH bond on the beta carbon atom here. Okay, this will occur only when the hydrogen and chlorine atoms both are in the axial position. We need axial position here. That is why it is known as diaxial, trans diaxial geometry. That is the geometry preferred for E2 elimination reaction. That means E2 elimination, it must occur from a less stable conformation. Because the chlorine in the axial position means there is a less stable conformation here. We have seen that because equatorial chlorine, that is more stable rather than the axial chlorine. But E2 elimination will take place only from a conformation where the chlorine atom is axial. Correct? So this is very interesting. So let us discuss it further, how it will be happening, So that is trans diaxial geometry for the E2 elimination. Okay, now let us see. We will just draw here which are the beta carbon and all here itself. So this is our beta carbon here. Okay, now here this is the alpha one. So here our axial hydrogen, this is a beta carbon atom here. This is a axial hydrogen is here. Correct? So this is the equatorial hydrogen. Correct? So this is the beta carbon atom. This is of course alpha carbon, you know that. Now here, so we have an axial hydrogen is there, an equatorial hydrogen is there. Correct? So this is again another beta carbon atom here. Okay, two beta carbons here. So conformation X, we can say this conformation, it is X, we can say. Now here conformation X, here what happens here, this beta carbon CH bond here, beta CH bond and CCl bond, okay, they are not in the anti-periplanar position here. That is CH bond, CCl bond, okay, they are not in the anti-periplanar. Anti-periplanar position. Correct? That is the beta CH bond here, the beta CH bond and the CCl bond here. This is the beta CH bond here and the CCl bond. They are not anti-periplanar to each other. So what will happen here? This conformation X, this cannot give an E2 reaction. So there is no E2 reaction. No E2 reaction here. This conformation cannot give an E2 reaction here. But now if we come to the other conformation, let us see. So here the chlorine is axial. Now we have hydrogen over here. Again an axial hydrogen here, beta position. Now there is another hydrogen over here. Is another beta hydrogen over here, axial one. Okay, now this can react. This is a base here. This base can take this proton here. Then all these reaction, E2 reactions are possible here. See, this is the difference between these two conformations here. So this conformation Y, we can call it Y or whatever it is there, conformation. The other conformation, that is the chlorine is in the axial position. Okay, so this is conformation Y. So here the chlorine in the axial position, the hydrogen, the beta hydrogen and chlorine, they are trans-diaxial position. So this is trans-diaxial position. Trans-diaxial geometry here. Here the E2 elimination takes place and we will be getting a alkene here. So what is the nature of this alkene being formed? Okay, so the double bond. This is the double bond being formed here. So this is the alkene being formed. So this can be the planar structure we can draw like this here. So this will be like this. Correct? So the beta CH bond and the CCl bond, they are trans-diaxial. So E2 elimination occurs here. This is the E2 elimination. It is occurring here. Correct. Now that is trans-diaxial position. We call it trans-diaxial positions here. Now, this is something very interesting here, because the rigidity here. That is the stereochemical arrangement. It is very, very rigid here. It should be a trans-diaxial and all means it is a rigid stereochemical requirement. So what will happen? If there is a rigidity here in the stereochemical arrangement requirement, then the regioselectivity of the E2 reaction of the substituted cyclohexane, it will be affected here. Okay, that is the regioselectivity of the, what is meant by regioselectivity? We will discuss it in subsequently now. Regioselectivity of the substituted cyclohexane, it will be getting affected. Okay, so that is the difference here. That is the rigidity of the requirement of the stereochemical requirement for the E2 elimination reaction to take place. It will affect the regioselectivity of the E2 reaction of substituted cyclohexanes. Now we can see some examples here. I will just change this page. Substituted, say, so let us see one compound, say 1-chloro, then 2-methyl, 1-chloro, 2-methyl cyclohexane. Let us see how it looks like. Okay, one example here. So 1-chloro, 2-methyl cyclohexane, the planar position ring, we can represent it in this fashion. That is, chlorine, it can be on a wedge here, and this methyl group, it can also be on a wedge. This is one possibility here. This is the trans form. Cis form. Both the things are on the above the plane of the ring here. So this is the cis form. Then we have the trans form. The trans form will be either of these group, it will be below the plane, and one will be above the plane here. Okay, so this is the trans form. Correct. Cis isomer and trans form. Now let us see the cis isomer, the chair conformations of the cis isomer, how the reaction will take place here. Let us see we will draw the cis isomer here. I'll just change this one. That is 1-chloro 2-methyl cyclohexane. That is what we have been discussing over here now. So this is our chair form here. Now we have this chlorine. That is the cis isomer we are just considering here. Then we have this hydrogen over here. That is chlorine in the equatorial position. Cis isomer conformation we are writing here. One group will be axial and another group will be equatorial. That is the conformation here. We are just going to draw now. So then this CH3 group here. CH3 group over there. Okay, that is an axial CH3 group, methyl group. Axial methyl group here. This is the equatorial hydrogen, of course. So axial methyl group and equatorial chlorine. That is cis isomer, cis conformation. We can say one group axial and one group equatorial. So we can say this conformation, say A or B or whatever it is there, you can just add. So here there will be ring flipping. So ring flipping, it will form another compound here now, another conformation here. Something like this. Okay, now here ring flipping, chlorine becomes axial here. Chlorine, that is during the ring flipping, the cis trans positions do not change. We have learned that thing. Now only the axial becomes equatorial and equatorial becomes axial during ring flipping. Correct. So here conformation A, the chlorine in the equatorial position and methyl group in the axial position. During ring flipping, what happens? The equatorial chlorine will become axial chlorine and the axial methyl group, it will become equatorial methyl group here. Okay, so this is the thing. You see, this is the conformation B, we can say here. A and B. Cis, this is the conformation for cis isomer. All these are cis. Correct? Cis means cis isomer, one group axial and one group equatorial here. Cis isomer. Now, cis isomer exists two conformations here. Okay, these two conformations, say A and B, we have written here. Now, each one has got one group axial and one group equatorial. Correct? So, E2 reaction, it must occur from conformation B. Why? because which has got an axial chlorine atom here. Most important point, because conformation B has got an axial chlorine atom, therefore E2 elimination takes place here. Okay, now let us see this, let us analyze this conformation in detail now. Okay, that is conformation B. So how many axial hydrogen atoms are here? How many axial hydrogen? 2 axial hydrogens will be there. Okay, something like this we can draw here. So here we have this chlorine, then that is the axial chlorine is there, H is there. Then we have this equatorial methyl group. Now this hydrogen, we have got 2 hydrogens here, axial hydrogens. So we can just mark it here, HA, and this can be HB. Correct. That is 2 axial hydrogens. The elimination can take place with both these hydrogen atoms here. Now, if we react, if this HA and chlorine, there is elimination means what will be the nature? That is minus, say, HACl. If it is minus HACl, then we have what is the alkene being formed here? So this is the double bond here. Okay, so here there will be the methyl group, CA3. That CA3 will be intact. The double bond, that is HA. This hydrogen is being used, hydrogen marked as A here, HA, and the chlorine goes here, HCl elimination. That is, it is a disubstituted alkene. That is a minor product here. So how will you draw this minor product disubstituted alkene here? This is the product here. Okay, this is a disubstituted alkene. That is a minor product. That's a minor product here. Now, if if this HBCl, if this hydrogen B, it is being used here for elimination. So, what will be the type? Here, the double bond, it will become here. There is a difference here. Okay, then there will be this CH3 group here. So this will be formed from here, how? Minus HBCl. So minus HBCl, we will be getting a tri-substituted alkene. So this alkene will be a tri-substituted alkene here. So this tri-substituted alkene, it is the major product. Other one is the minor product and this is the major product here. Correct. This is the conformation B of the cis isomer here. Okay, the cis isomer means two different axial beta hydrogen atoms are there here. We have marked it as HA and HB here. Both hydrogens can react. In the E2 reaction can occur at two different locations here. Okay, it can proceed in two different directions, E2 reactions here. That is to give two different types of alkenes are possible here. Okay, the major product, it will contain the more stable tri-substituted double bond. Okay, that is the major product here. It will be the, which one? The major product contains the more stable one. The more stable will be the tri-substituted double bond. As predicted by which rule? There is a rule called ZAITSEV rule. ZAITSEV. ZAITSEV rule. So the ZAITSEV rule says, what does it say? What is the ZAITSEV rule? Let us see what is the ZAITSEV rule here. So this ZAITSEV rule, it actually, it is a Russian scientist, it can be written ZAITSEV, we can write here, or we can write here, say, ZAITSEV, ZAITSEV. Different textbooks we can give in different ways it is being written now. So the ZAITSEV rule, so it helps in forecasting. So what will be the alkene which will be predominantly formed there? Okay, we have to predict. We can predict which alkene it is a more likely product in this elimination reaction. So in the dehydrohalogenation of alkyl halide reaction. Okay, now having two or more different beta carbon atoms, it can yield a mixture of alkenes. We have seen it. So a mixture of alkenes can be formed. So when this occurs, one of the products, it will usually predominate, or it will be the exclusive product, we can say. That is, the major product here, it will be the more stable product. Major product means that will be the more stable product here. That is one with the more substituted double bond. In the alkene with more substituted double bond, that will be the major product because that is a more stable product here. That is what the ZAITSEV rule says here. That is the major product in the beta elimination, it has the more substituted double bond. That is ZAITSEV rule here. Now, a reaction is known as regioselective, that we have been telling some time back, regioselectivity. So the regioselectivity means the reaction, it is regioselective. So when it yields predominantly or exclusively, we can say, one constitutional isomer, one structural isomer, when more than one is possible. That is, in the reaction, more than one structural isomers, it is possible. So the reaction is regioselective when it will yield predominantly or exclusively one constitutional isomer when more than one is possible. So E2 reaction is a regioselective reaction because the more substituted alkene, it will predominate here. So that is the ZAITSEV rule here. Now let us see in the case of substituted cyclohexanes, what is the position here. Now we have seen the cis isomer. Now let us see the trans isomer. Here it will be interesting. The trans isomer, the ZAITSEV rule, we will find it slightly difficult. Let us see. So in the trans isomer, we can again, just like in the case of cis isomer, we can draw two conformations here in the case of trans isomer. Okay, so this is a di-equatorial one. Trans will be di-equatorial. So here we can say this chlorine equatorial position, and here hydrogen is there, then it will be CH3 group here, that is di-equatorial. This conformation it is known as di-equatorial. Okay, so this will be flipping, ring flipping. It can form like this here. So this chlorine, it will become axial chlorine, and this methyl group, it becomes a axial methyl group here. That is di-equatorial, it becomes diaxial. This is a trans isomer. Trans isomer, that is two conformations. Say we can say this will be, we can just give the names here, C and D and all we can give. Just two names we can give here. Okay. So C and D, C having two equatorial substituents here. That is chlorine and methyl group both are equatorial here in the case of C, and in the case of D here, two axial substituents, that is a methyl and chlorine, Cl, two axial substituents. So E2 reaction, it must occur from conformation D because it has got axial chlorine. Okay, E2 reaction, it should occur from conformation D. So conformation D, it contains one axial, the chlorine atom is in the axial position here. Okay, now let us see how this reaction take place here. So what will be the nature of the compound here being formed, the alkene being formed here? Let us see. So minus HCl, correct, because the chlorine that will be eliminated here. That is equatorial hydrogen, it does not react. Equatorial hydrogen here, only one beta axial hydrogen we can say that can react here. Okay, so the product being formed will be so this methyl group is here. Here, this is the double bond. This is the alkene being formed here. Okay, now this is the alkene. Okay, minus HCl. So CH3 group here, because there is an equatorial hydrogen here. This equatorial hydrogen, this does not react here. Okay, so this is the alkene being formed here. So this will be the planar structure, how it will look like. We can say here CH3. So this is the di-substituted alkene. This is the only product being formed. Only one product is being formed here. That is the trans isomer having two equatorial substituents and di-equatorial and diaxial. We have seen that. Okay, in this one, we will be getting so here there is a hydrogen. That's all I am not writing here. All these things are here. This CH3 group is important for us, and chlorine, Cl is important here. Okay, now equatorial hydrogen does not react here. Correct? So here we will be getting a single disubstituted alkene. There is no other product being formed here in the case of trans isomer here. Okay, now we have seen the cis isomer. Now because this conformation D, it has got only one axial beta hydrogen. Conformation D has got only one axial beta hydrogen. Correct? Because the other one is a methyl group here in the beta position. There is a methyl group is there. Therefore, conformation D has got only one axial beta hydrogen atom. So E2 reaction will occur in only one direction. Okay. So to give a single product having the disubstituted double bond. So this is not as per our ZAITSEV rule. Okay. ZAITSEV rule says the more substituted, that a trisubstituted product should predominate here. Now E2 reaction here, it proceeds only in one direction here to give a single product. It is a single product having a disubstituted double bond. So ZAITSEV rule, it is not being followed here. So E2 reaction, it requires the hydrogen and chlorine to be trans and diaxial. Trans diaxial position. And with the trans isomer, this is possible only when the less stable alkene is formed as the product here. So this is the most important point here, the deviation. Less stable product. That is deviation from ZAITSEV rule. Okay. Deviation from the ZAITSEV rule we can say here. That is the less stable disubstituted product alkene is being formed here. Correct? E2 reaction requires the hydrogen and chlorine to be trans and diaxial. Correct? And with the trans isomer, this is possible only when the less stable alkene is formed as the product here. Okay, that is the more substituted alkene is not necessarily the major product, as in the case of an E2 elimination reaction with the substituted cyclohexanes. With substituted cyclohexanes, there is no hard and fast rule. The more substituted alkene should be the major product here. Okay, therefore, that is a substituted cyclohexane alkene having a trans diaxial arrangement of hydrogen and X halogen atoms here. The more substituted alkene is need not necessarily be the major product. Correct? As in the case of E2 elimination reaction with the substituted cyclohexane having a trans diaxial arrangement. Therefore, in this case, the ZAITSEV rule, it is not followed. Okay, so thank you very much for listening.